Alright, hello everyone. Welcome to Kinematics in One Dimension. We'll be exploring kinematics in 2 and 3 dimensions next week. But for right now, the main goal is to get you used to kinematics and the ideas of motion, acceleration, velocity, and position. So without further ado, let's talk about the motion of objects. The motion of objects, whether it be baseballs, automobiles, joggers, cars, even the sun and the moon, it's an obvious part of everyday life. Everything is moving. It was not until the 16th and 17th centuries that our modern understanding of motion was actually established. Many individuals contributed to this understanding, particularly Galileo Galilei, who actually was the first person to think that force was proportional to acceleration, which gave rise to our second main guy, Newton's formula F equals ma. That's what the entire exam is named after. Now, the study of motion of objects and the related concepts of force and energy form the field called mechanics. Mechanics is customarily divided into two parts: kinematics, which is the description of how things move, and dynamics, which is the description of why things move. And it explains kind of the forces, torques, and underlying things that allow motion to actually occur. In this lesson and in the next lesson, we're only going to deal with kinematics, but dynamics will soon come up with our discussions of momentum, energy, and force. So for now, we're only going to discuss objects that move without rotating. So there are two main things that I want you to get accustomed to before we start delving into kinematics. The first thing is that we only discuss objects that don't rotate, and we call that motion translational motion. Now, as you can see in figure A, this ball undergoes pure translation as it falls, whereas in B, it is rotating as well as translating. So you can see that at time t equals t1, ti, it is in that position, however many units above, and in this position it's fallen a little bit. But as you can see that this point P remains constant. It has not shifted. It hasn't rotated at all. How you know that there's rotation is when you have this point P over here and it's shifted. That same point that was once here at time t equals ti is now here at times t equals tf. And it's rotated. But not only that, the ball has fallen a little bit. These lines are supposed to indicate wind, or like the ball is moving. So in B, you see rotation as well as translational motion. Here you only see translational motion. And A is what we're going to be focusing on in kinematics for the most part. We're going to introduce you to rotating a little down the line, but for now, for this lesson, we're going to be mainly dealing with translational motion. We also often use the concept or model of an idealized particle, which can be considered to be a mathematical point and to have no spatial extent. In other words, it doesn't have size. And why do we do that? Well, to avoid complications with things like center of mass. For example, if you have a car, and as we're going to get to in a moment, there will be problems with a car. Sorry for the horrible drawing, but there will be problems with cars moving that way at whatever miles per hour, or decelerating that way, negatively accelerating that way at negative 54 miles per hour, whatever. But it's really a pain and a hassle to keep on drawing a car over and over. So for notation, we're just going to use this dot. And that dot is going to represent everything. Not just the car, but let's say a ball is being thrown up. The acceleration, as you will slowly learn, is g equal to negative 9.8 meters per second squared. But let's say the velocity is thrown up at 10 meters per second. The idea is this notation is that you can you can describe the object in question, whether it be a ball, a rocket, whatever, and you can do it very effectively, cleanly, and without actually having to draw a realistic description. Now, of course, you can, if you want to distinguish this with this particle, you can label this one rocket, and you can label this one ball. But those are just some notational things that you might want to consider. The particle model is useful in many real situations where we are interested only in the translational motion and the object size is not so significant. So, for example, again with the car thing, it's not like as if the car is going to be rotating. So it's much easier for us to depict the car as a particle because there's no rotation or any two-dimensional motion happening, or two different aspects of motion happening. For example, another example is that we might consider a billiard ball or a spacecraft traveling towards the moon as a particle for many purposes. And it just makes it easier as physicists to deal with stuff.